We will now continue with our study of electric potential by solving problems using the results we obtained in the last class. Now, to begin with, let's do a review. Tell me, what is the expression for electric potential at a point distance r from a charge q? Alright, the electric potential at a distance r from a charge q is V equal to kq over r. Now, if the charge is a positive charge, the potential will be positive, and if the charge is a negative charge, the potential will be negative. Now, another relation I would like you to know: what is the relation between electric field and electric potential? Can you recall that equation? What is the relation between electric field and electric potential? Well, the famous equation we talked about yesterday, dV by dr. E, electric field, is negative of the rate of change of potential. E equal to negative dV by dr. Right. And when you write this specifically for the x direction, we will say Ex equal to negative dV over dx. That means electric field can also be measured in the unit called volt per meter. Now, if you ignore the negative sign, I can write dV equal to E dx. Well, all these relations you must be familiar with in order to solve problems. Alright, let's start solving a problem. Example 1. An infinite plane of surface charge density sigma equal to positive 2.5 microcoulomb per meter squared is in the YZ plane. What is the magnitude of the electric field in Newton per coulomb and in volts per meter? What is the direction of the electric field for positive values of x? Well, actually, this is from a previous lesson that we had already done. It's a very simple problem, is that right? Okay. What we have is an infinite plane charge that is in the YZ plane. By now you know this is the x-axis, the y-axis and the z-axis. The plane is in the YZ plane and the surface charge density is positive 2.5 microcoulomb per meter squared. Now, electric field due to an infinite plane of charge density sigma. Now, what is the expression for electric field near an infinite plane of charge density sigma? We did that in the 2 classes ago. Will be E equal to sigma over 2 epsilon naught. That means the electric field at any point near that charge will be sigma over 2 epsilon naught. We know sigma, that is 2.5 microcoulomb per meter squared, 2.5 times 10 to the negative 6. Epsilon naught is 8.85 10 to the negative 12. That gives the electric field 1.41 times 10 to the 5 Newton per coulomb. Well, what's the B part? Well, this is in Newton per coulomb. Can you express the same electric field in volt per meter? If you remember the little assignment I gave you, extra credit assignment last class, to show that Newton per coulomb and volt per meter are the same thing. So 1.41 times 10 to the 5 Newton per coulomb is the same as 1.41 times 10 to the 5 volt per meter. And what is the direction of this electric field? Well, for positive values of x, the electric field is directed in the positive x direction. Alright, let's look at another part of the problem. What is the potential difference VB minus VA when point B is at x equal to 20 centimeter from the charge or from the origin? We assume that the charge is at the origin, and point A is 50 centimeter from the origin. We need to find the potential difference between these 2 points. Well, you remember that equation. Delta V equal to negative E dr, or delta V equal to negative E delta R. Or specifically for the x-axis, we can write it as delta V equal to negative E dx. So this dr is the distance between the 2 points. Delta V corresponds to the potential difference between the points, and E is the electric field. So the potential difference between the 2 points is negative of E dr. VB minus VA. Delta V is potential difference between the points A and B. VB minus VA equal to negative E times x1 minus x2. dr is x1 minus x2. And this is our x1 and this is our x2. x1 equal to 0.2 meter. x2 equal to 0.5 meter. So we have a negative E, negative 1.41 times 10 to the 5. We just calculated the electric field, times x1 minus x2. That will be 4.23 times 10 to the 4. You notice that the two negatives, 0.2 minus 0.5 is negative. And that negative with this negative become positive. So tell me, which of these 2 points is at a higher potential? Alright, anybody tell me which of the 2 points A or B is at a higher potential? Well, if you remember, the direction of the electric field is the direction of decreasing potential. Therefore, B is at a higher potential than A. Alright, let me also ask you, what is the basic definition of potential difference between 2 points? Remember, a volt. What is the meaning of a volt? Volt is joules per coulomb, work done per unit charge. Now, the potential difference between points A and B is 4.23 times 10 to the 4 volt. Means in order to move 1 coulomb of charge from A to B, we need to do this many joules of work. So 4.23 times 10 to the 4 joules of work need to be done to move 1 coulomb of charge from A to B. Alright, that's the meaning there. So we found the potential difference VA minus VB. Alright, how about the next one? How much work is required by an outside agent to move a test charge Q0 equal to 1 nanocoulomb, 1.5 nanocoulomb from A to B? Well, if you understood what I said earlier, potential difference between A and B is 4.23 times 10 to the 4 volt. Means in order to move 1 coulomb of charge from A to B, the work that needs to be done is 4.23 times 10 to the 4 volt, 10 to the 4 joules. Therefore, if you want to move 1.5 nanocoulomb from A to B, what is the work that needs to be done? VA minus VB is a measure of the work done per unit charge. that is moved from A to B. Therefore, work done to move 1.5 nanocoulombs will be work done per unit charge multiplied by that charge. That will be W equal to 1.5 times 10 to the negative 9 coulomb, the amount of charge multiplied by the work done per unit charge, and that is 6.35 times 10 to the 4 joules. So here we clearly use the relation between electric field and potential difference. Okay, let's look at another problem.